So thank you, Deborah, for organizing this, which is such a fabulous thing, and Taylor for sharing this with me. And thanks to Emily and Peter as well. And thanks to all of you for being here with me on this beautiful, balmy February evening. As the science side of this conversation originates with a geologist, I thought I would put together a version of my work that looks at it from a geological perspective. And please forgive me, scientists, for errors and omissions. This is easier than you might think because geology was at the center of things when I started photographing landscapes about 30 years ago, following a visit to Iceland, where this is. That's the main road, by the way, in Iceland, with my father, who is a sort of amateur geologist and was doing research there. His reflections on time and geology continue to influence my thinking. And here's one idea. He has written, if you free yourself from the conventional reaction to a quantity like a million years, you free yourself a bit from the boundaries of human time. And then, in a way, you do not live at all, but in another way, you live forever. I'm still working on that. Iceland, as you likely know, is a hot spot on a spreading center, a place where the Earth is born, a place where in real time you can see geology happening openly, easily, excitingly, which, trust me, I have not always found to be the case. Hotspots are fun and fascinating places, as their name implies. And in Iceland, working with another photographer, Virginia Bean, I began my exploration of meaning in visual meaning in landscape photography. Since this is not the context for a full look at my work, I am giving you a very abbreviated version, or the beginning and closer to the end. So in this picture, this is me actually with my 8x10 view camera, which became my tool of choice, which is 19th century technology with better optics. And then all that stuff on the ground is film holders and a carpenter's level and all the things you need to make this contraption work. So essentially it's a mahogany box on a tripod, and I'm using black plastic as a dark gloss. Things have improved since then. In using this really inconvenient means of production, I am also honoring my desire to use photography as a recorder of facts. We all know that photographs lie, just as we know that a single image is extracted from the unbounded flow of real life, and is thus a partial record. Yet there is a power of description attributable to the recording of light on film, to the photograph itself as a straightforward recorder of the data available in that fraction of a second, that enthralls me still. So in the second year we worked in Iceland, we made this picture of the Svartsengi geothermal hot water pumping station, also known as the Blue Lagoon. Though we couldn't have said it then, this picture was emblematic for us on a number of levels. It is a photograph of something benign, geothermally heated waters being pumped out of the ground to supply the people of Reykjavik with hot water straight to their taps. But paradoxically, to the eyes of someone who grew up in New Jersey, or almost anywhere in the industrial world, it looks frightening and malevolent. It is about leisure, and it's also about industry. Beauty and fear are held in tension. In my opinion, this place is much more fearsome now because it has a lot of infrastructure around it, including a hotel, a swim-up bar, cocktail waitresses with little bow ties, and back then it was just a beach with an unusual view. Later, we worked in Hawaii, another hotspot. This image depicts the rim of a volcano being reduced to red sand by the waves, mother and baby both less than blips on the scale of geologic time. For 12 years, Virginia and I worked together photographing landscapes all over the world. As we worked, we came to recognize that no part of the Earth's surface is unaltered by human activity. That the idea of an external, autonomous nature is a myth. Our interest lay in looking at the ways in which people are engaged in a long and complex dialogue with the land. This is a photograph that we made in Hawaii at that time, which was the early 90s. And so lava is flowing underneath the what you're seeing here. And it is pouring into the ocean, and it's about 2,000 degrees pouring in there. And you see, I guess, you see back there the little sticks. They are emblematic of the transience of human efforts, because that was the former visitor center. And now those cones are put up to keep us back from making this picture, but it didn't work well. Later, we found other volcanoes. This one on the Strip in in Las Vegas. The lava here is prehistoric water pumped from the aquifers in one of the driest areas in the United States. Consider the evaporation rates on this irreplaceable resource. So most recently, I've been working on my own in the Desert West, often thinking about the notion of the Anthropocene, a term used by some geologists to recognize the profound impact that human activities have on the Earth. In my work, I am confronted with evidence of extraction and preservation, human and geologic time, attempts at improvement and the repercussions of degradation, and what it is we leave behind. In this image, you see two timescales, as in many of the images, both geologic and human. This is today a harsh and barren landscape in Utah, but in the Cretaceous, it was the bottom of the Mancos Sea. For a photograph, this monochromatic world makes a perfect canvas for the activities of weeks and years. So there are footsteps, human footsteps, animal footprints, the trails of ATVs, and erosion. Something similar could be said about the way time can be seen in the Lavender Pit, a silver and turquoise mine in Bisbee, Arizona. And this one is the Sonoran Desert, and it's a copper mine. And what you see is tailings from the copper mine at the top of the picture. I like to think about this sentence from the writing of the great naturalist John Muir. When we try to pick out anything by itself, we find it hitched to everything in the universe. Muir would not have imagined the scale at which that sentence carries meaning now, when mining and the resulting carbon release impacts not only the local fish population, but also the pack ice in the Arctic and thus polar bears, just for instance. So large-scale human activities and their attendant release of carbon, this is fracking against the Wind River Range in Wyoming, and their attendant release of carbon are responsible for the impacts now visible on the landscape in the form of droughts, flooding, or rising sea levels, quite literally causing infrastructure to drop into the sea. I find myself beset by questions that seem to have few direct answers. Even if answers are available, we, as the people and a government, seem unable to agree on facts and thus are prone to inaction. I look at what we are doing in the landscape and at the multitude of ways we see our world altering and think about our collective sense of powerlessness. As I work, I ask myself what sort of stewards we have been of the land. How do we decide what should be preserved or exploited? How do we define wilderness and what it means to us? What is our notion of nature's perfect moment, and how do we seek to recreate it? What is our responsibility in our human time to the other creatures that share the earth with us and to each other? How does history, personal or political, shape our vision of nature and place? How do we link ourselves to nature in an environment now known more for degradation and the fear it engenders than for the pleasures and beauties it inspires? Treat the earth well, a Native American proverb reminds us. It was not given to you by your parents. It was loaned to you by your children. Thank you.
I would like to say to start that this is a real treat to be able to talk to people who are interested in visual art and in landscapes, because so much of what we do in earth sciences, and in particular in my area of the earth sciences, really starts and ends with observations of the natural world. And so I think there really are a lot of similarities. And a couple of things that you said, Laura, really underscored that. The first was this quote you gave us about being able to compartmentalize and put aside the meaning of a million years in an attempt to try to transcend time. I think I'm still working on that, but as you'll see in a minute, maybe we're making a little bit of progress. The other thing you said that I think illustrates some of the similarities between geologists and photographers in particular is that apparently we share the characteristic that, based on your photo from the active volcano flows in Hawaii, sometimes we decide that do not enter signs don't apply to us when we're doing field work. When I tell people that I study landscapes, if there's no context, oftentimes they assume I mean this, which is of course very beautiful. But the kind that I spend most of my time thinking about is the natural kind. And when a geologist looks at a landscape like this, of course we see beauty, and that motivates us to try to understand it more. We also see a series of different systems that are nestled within this landscapes. The steep slopes shedding sediment down to the floodplain of the river, the vegetation that borders the river, the active channel transporting sediment downstream, rising and falling with the flood. And what we try to do is understand how all those component systems operate individually, describe them mathematically if we can, and put those back together to try to understand not just how a landscape came to be the way it is now, but if we can do that, we might also be able to predict how it might respond to changes in the future. And so the theme behind just about everything we do in my research group here at MIT is we try to read Earth's past by looking at landscapes and studying them to try to understand Earth's future. And our reasoning behind that is that a planet's history is written in its landscapes. And we don't just mean rocks, although of course those do come into play, but we also mean climate and plate tectonics and life. All of these things come together to determine the trajectory of a planet's history. And we try to read landscapes, and especially patterns in landscapes, like you see in some of these images here, to try to understand what has happened in a given place. What I'd like to do now is step through a few examples to show you what I mean. And I'm going to start with some of the finest scales that you see in these images here, centimeters. And then we'll work our way up to progressively larger and larger scales and end with some of the broadest scale landscape patterns that we work on. So I'm going to start with something that you probably have all walked on, which are ripples in sand made by waves. So I'll give you your first homework assignment right at the beginning of class here. Your homework is to go to the beach so you can experience some of these things. If you're local, you might want to wait a few months, although if today is any indication, get out there while you can. And so I show you this pattern from a natural landscape first. At present, ripples that have evolved very recently. But then we also find, from a geologist's perspective, that since wave and water and sand have been around for a long time on Earth, so have these ripple patterns. So what you're looking at here are ripples that formed over the course of a few tens of minutes to a few hours, almost 2 billion years ago, and were then preserved in rocks for someone to encounter in the Northwest Territories in Canada at the present day. If you're especially intrepid and you go across the street after a lecture tonight, you might also see that ripples are common on MIT's campus. This is right across the street of the Building 68 lobby. The irony here is this is the biology building, not the earth science building. Our excuse is that we don't actually have a lobby to put them in. And so we take patterns like this and ask, what can we tell about the environment that formed them? Can we replicate this in a controlled setting? And so one example of how we do this is to perform laboratory experiments. So in a warehouse here on campus, we built a wave tank where we can create features like this in a controlled environment. And I'm just showing you one example of a time-lapse animation where you can speed up time. These form pretty quickly, but here you're seeing things sped up by a factor of several here. And so you see these ripples spreading out from an initial bump as the flow that's washing back and forth carries this perturbation in the sand over a wider and wider range. So that's an example of how we do this kind of experiment. But we do even more controlled experiments where we start with one set of ripples and we change the waves to make them take on a new pattern. And so what you'll see as this time-lapse movie progresses up on the top is that these initial parallel ripples deform and you start to form a different pattern. You can see these little segments of ripples start to form in between the others, and you make patterns that look a little bit like hourglasses with ridges in between. And as you can see on the bottom, when we look back at ripples that are hundreds of millions or even billions of years old, they're those same patterns. So now we can look back at these ancient ripples and say, at that point in time, 2 billion years ago, either the water had just gotten deeper, perhaps the tide was coming in, perhaps a storm was coming up and there was some storm surge, or the waves were getting smaller and the winds were calming down. So we have a sense of how things were changing even very long ago in geologic time. So let me move on now to a slightly broader scale. And we're going to look at a few features that we see repeating in landscapes. So this is one thing we try to do. In addition to looking for patterns, we say, what kinds of common features do we find in lots of different places, and what do they tell us about common processes that are occurring in landscapes? So this is an example from Northern California. You see rivers that have cut into the rock, forming this landscape. The landscape is draped with soil over top of that rock. There's vegetation growing on the top, and there are things that live in that soil. And one of the remarkable things about landscapes is that in many cases where you see soil, you see a finite end to the river network. You see where the channels stop here, and the spaces in between are rounded. They don't have infinitesimally fine river networks dissecting the whole landscape. If they did, the soil might be gone pretty quickly. And one of the reasons why they don't is because we have organisms that disturb and stir the soil and create new soil from bedrock, and they tend to smooth out any little rivulets that start to cut into the surface. So you could think about California pocket gophers perhaps as some of the original soil conservationists. And we see some of those same features even in very different environments where life is somewhat more sparse. Again, a rounded hill slope, which suggests that the rock there has been broken up to make soil, has been moved down slope by some sort of mechanical disturbance process. Can anyone guess where we are? Well, I hear a few whispers that might even be right. I'll tell you, here's a hint. Nobody in the room has done field work here. I'm trying to trick you a little bit by playing with Photoshop. Yeah, exactly. So you change some of the colors, and suddenly the landscape looks a lot more alien. But if you just look at the form of the topography, it actually is shockingly familiar. So no little green gophers, presumably. So what's doing it here? Probably some combination of ice and salt acting over a longer period of time, but nonetheless creating similar features. So now let's continue to even broader scales, and I'm going to illustrate some of the ways that we use images and technology together to study landscapes and to map topography. A technology that's just been available to us for the last couple of decades is laser scanning of the landscape. You hear a lot about self-driving cars in the news these days, including on this campus, right? And the technique that they use to make a constantly evolving map of all the obstacles around them is essentially the same technology we can use to scan the landscape. As an aircraft flies overhead and scans the topography with a laser, it hits the ground. Sometimes it'll hit the top of the tree canopy. Sometimes it'll go through and hit the ground surface and bounce back. And the amazing thing that we can do now that we couldn't do before is to digitally remove some of the vegetation so that we can actually see what's underneath. And you can see the landscape laid bare in a way that was just not possible before. You can see the topography with all of its scars and warts exposed, which are exactly the kinds of things we like to measure and understand. So this has changed the way we can do geology at Earth's surface by more clearly revealing some landscape patterns and allowing us to measure them more precisely than we could before. So we can do in a day what would have taken years of surveying to do previously. You see all of these ridges and valleys that are aligned kind of like the teeth on a comb. They all have a very even spacing. And we are able to measure that and also show, through the use of computer simulations based on the measurements we make in the field, that the reason you get these very evenly spaced valleys is that there's a competition between all the rivers that cut into the rock and the soil being stirred and smoothing the landscape. I'm going to expand out one last time here to an even broader scale and show you one of the most striking landscape patterns that you're likely to see. And this also is something you've probably also seen if you like to take the window seat on an airplane, and that is river networks. They form the skeleton of the landscape, and what I mean by that is they determine the structure and the arrangement of all the valleys and the ridges that define the topography. The rest of the landscape is built on this lattice work. Why do these branching river networks form? How do they evolve through time? These are the kinds of questions that my group asks and tries to answer. We do field work, we make measurements of topography to do this, and we also create mathematical models that we can use with the help of computers, where we can simulate the evolution of landscapes and the development of river networks over quite long periods of time. So again, this is an effort to try to put aside what a million years means so that we're not constantly blown away by the enormity of it and reduce it to something that we can try to understand and maybe transcend time a little bit by doing that. And now to close, I want to bring this back to the present and to humans, because the thing that I started off motivating this at the beginning was the desire to not just understand how landscapes have come to be the way we see them now and what physical and chemical mechanisms have done that, but also how an understanding of those mechanisms will allow us to understand or predict what might happen in the future if things change. So I've also showed you a lot of mechanisms that operate very gradually to change landscapes, but that's not always the case. They can be episodic, they can be sudden as well, and landslides are an example. One project that my group has been involved in is coming up with better mechanical models of landslide occurrence, especially during heavy rainfall in landscapes like this one, which, as you can see, has been altered by clear cutting. And so we'd like to understand how, if landslides happen during large, heavy rainstorms, how that response might change if those rainstorms become even more intense and more extreme under future climates. So I'll close there as a way of bringing this back to the intersection with the human sphere, and perhaps that'll provide a segue to our discussion. So thank you.